although there are different data link layer protocols, all the protocols they use header, data, and trailer as part of the frame structure, and therefore they send the frames to facilitate the shared medium amongst multiple nodes, as we can see here. For each node will encapsulate the frame and will change both the header and the trailer at every local area network to facilitate the transmission across a specific medium type. So now we need to talk about the format of that frame for different standards. All these standards, they use header, which roughly contains the start frame, as we said, the address and the type of the lens, and sometimes it includes other control fields, which again which provide some flow control to the frame transmission, and then the data, and then the frame, and then the frame size. In addition to that, the control field, as we said here, includes some kind of a logical connection field, or a flow control field, or congestion control fields, which can be detailed depending on the type of standards that we talk about. The data link layer as well provides addressing. So if we want to send from A here to E, then we have to provide some kind of an address in the frame that identifies that this frame is distant to E. In which case we use physical address, or MAC address, as we have talked about last time. In a logical point-to-point topology, we don't need to provide any addressing or we don't need to provide identifier for between multiple nodes, because basically the connection is between only two nodes, in which case we use only one byte to indicate the direction or the destination on the other side, and that's it. So we don't need to provide a physical address like the case of multi-axis technology. The trailer is simply frame check sequence, and the frame check sequence is used to provide some error detection. So the frame check sequence here contains a certain code which is used to detect any error that might happen in the data. So the code here is usually formatted using what we call cyclic redundancy code, or CRC. The cyclic redundancy code is a combination of the data which maintains the correctness of this data during the transmission. So if the receiver calculates the CRC and it finds that the CRC does not match the CRC in this field, then it realizes that the frame has some error, and in that case it needs to inform the source so that the source can send the frame once again. Again, the data link layer facilitates the communication between node to node across different types of medium, and in that case we can have wireless medium like this, or we can have point to point, we can have different technologies or different data link layer protocols, and we can see that for each type of medium here we can have a different frame which represents the technique or the data link layer protocol in that hub. So here we used PPP, here we used HDLC, here we used frame relay, and then we used Ethernet frame to send to the ultimate receiver. So each data link layer protocol defines the structure of the frame using the standard specification. And for the case of Ethernet, for example, this is the structure of the frame. And again, we see here the preamble representing the start of the frame, and it's also used for synchronization purposes between the sender and the receiver. The two types of address for the destination and source, each is 60 bytes to represent the MAC address, and there is the type field, which again indicates the higher layer protocol from the network layer, and of course the data which ranges in terms of size from 46 to all the way to 1500 bytes, and finally we have the frame check sequence for error detection. For the case of PPP, we find that the frame structure is rather simple. We have again a flag, which is in that case only 1 byte to indicate the beginning or end of the frame. We have the address, and as we can see, the address here is simply all F's to indicate that the destination is only one destination. So because PPP is used for point-to-point communication, and from one source the destination is always identified to be the other side of the link. So therefore the address is actually fixed and it's set as FF in hexadecimal. The control field is also affixed to indicate that there is no specific flow control or sequencing that is used by PPP, and again the protocol field to represent the higher layer protocol, whether it's IP version 4 or IPX or IP version 6 and so on. And of course the data, which in that case has variable size, it does not have any minimum or maximum limit, and then the frame check sequence, which is represented using up to 4 bytes to indicate the CRC codes. For the case of wireless, however, we see that the frame structure is significantly more complicated, and that's because of the fact that in wireless, of course, there is a high level of sophistication when it comes to how to avoid the collision, sending from one node to a wireless access point before sending to the other node. The control frame here is rather complex to indicate whether you have encryption or not, whether you have order or not, whether you have fragments of the frame, in which case the wireless frame or the frame is divided into smaller segments that each of them will have a sequence number and a fragment number. Here we also notice that the addressing is rather complicated. You have DA, SA, RA, and TA. All these are 4 types of addresses which not only include the source and destination nodes, but also they include the source and the destination access points that are involved in the communication. So you have 4 types of addressing. You have, of course, sequencing and segmentation, which are significantly different compared to the other formats of the frames. So that to actually summarize, we talked in this chapter about the network access layer in the TCP/IP protocol model, which is divided into the physical layer and the data link layer. In the physical layer, we talked about the physical components, including cables, UTP cables, coaxial cables, and fiber optics, and we also talked about encoding and signaling and encoding to convert the transmitted bits into codes, and then for signaling to convert it into a signal which is suitable to be transmitted over a copper line using electrical signal or light signal on fiber optics, or using electromagnetic waves on wireless technologies. We also talked about data link layer to facilitate the communication between 2 network devices on a local area network, and we talked about the frame structure, and we talked about the MAC sublayer or the medium access control, where we need to organize the access to the medium, whether in a multi-access fashion or a point-to-point fashion. For the multi-access fashion, we talked about contention-based transmission and controlled access, where we can eliminate the collision amongst the multiple points. That concludes this chapter, and see you next time.